Hello, welcome to the lecture module on optics. Today in the last class we discussed about the basics of reflection from a spherical mirror, and also we discussed about formation of images. In particular, we discussed formation of image of point objects. Then I briefly talked about extended objects, and extended objects can be thought of as comprising of large number of point objects, and therefore, point objects, getting the image of the point object is the first step. So, today we will see about extended objects. In particular, we will start with line objects or linear objects. So, and we will also obtain the mirror equation. So, image of an extended object. How to determine the image of an extended object placed in front of a spherical mirror? So, the issues are: what will be the position of the image? Will the image be larger or smaller than the object? Will the image be real or virtual? And will the image be erect or inverted? These are some of the issues which we will discuss today in this lecture. First, how to determine the image of an object. So, here it is. So, I have considered a spherical mirror here, I have considered a concave mirror, and AB is the object, this is the linear object or laterally extended object AB. So, to determine the image, as we discussed in the last class, we could consider any two rays which and find out which is the point of intersection. So, there are four different rays which could be considered. One, a parallel ray parallel to the principal axis, which passes through the principal focus here after reflection. A ray which is incident at the pole, which will get reflected, satisfying the law of reflection here, that is this angle here, the angle here is equal to the angle here. A third ray which we could consider is a ray passing through the principal focus. A ray passing through the principal focus or a ray coming from the principal focus will be rendered parallel, because a parallel ray will be reflected back in such a way that it passes through the principal focus, and by the reversibility of light, a ray passing through the principal focus and incident on a spherical mirror will be rendered parallel. A ray which passes through the center of curvature here, so a ray passing through the center of curvature will be reflected back along the same line, because we know that the line joining the center of curvature to the circumference, that is the periphery here on the mirror, is normal to the surface, and therefore, any ray which is incident along this line will be reflected back along the same line. Depending on the application, depending on the situation, we may consider any two suitable rays, any two rays to determine the point of intersection and hence the location of the image. We will see that there are certain circumstances when you can consider the parallel ray and one of these ray. Sometimes it is not possible to consider these, then you may consider these or whichever is the convenient depending on the problem. But any two of the four different rays, again here ray parallel to the principal axis, ray incident at the pole, second one here, one is this, 3 ray which is passing through the principal focus, a ray which is coming from the object passing through the principal focus will be rendered parallel, and the fourth, a ray passing through the center of curvature which will retrace its path. Now, let us take some examples geometrically, and so here are some of the examples. I have considered only two rays. So, this is the object AB, a ray parallel here is reflected passing through the principal focus, the ray which is incident at the pole is reflected satisfying the law of reflection, and here it is intersecting, and that corresponds to the image. A dash B dash is the image, A B is the object, C is the center of curvature, F is the principal focus, and P is the pole. We will follow this notation throughout this lecture. A second example that I have considered, note that the object that I have considered is beyond the center of curvature, farther than the center of curvature from the mirror. Now, I am considering another object which is between the center of curvature and the principal focus. A B is the object. So, a ray which is incident here. So, let me mark A B. So, A B has not. So, this is A. A B is the object, and a parallel ray and a ray which is incident at the pole, which intersect here now, and A dash B dash is formed here. An object between C and F, the image is formed beyond C, and we can see that it is a magnified image. We will discuss about the quantitative aspects of magnification and the location, etc., but right now we are looking at the geometrical determination of the position of the image. Next, I consider an object between the principal focus and the pole, and here is the object A B. The parallel ray is reflected through the principal focus, the ray through the pole is reflected here. As you can see, these are diverging, and therefore, they will never intersect in this direction. However, if we extrapolate it on the reverse direction, then we see that they intersect at a point here, which is A dash B dash. So, this is the image. It is as if these two rays appear to come from the point A dash. If you are looking from here, then it would appear as if A dash, the object point A dash, is located here, and therefore, the image is formed at this location A dash B dash. Since the ray does not pass beyond the mirror, so this image is called a virtual image. It is a virtual formation of a virtual image. We see that it is magnified image here when the object is between the principal focus and the pole. A fourth case, when the object is at the center of curvature. So, A B is located here. As before, we considered the two rays and they intersect at a point, and we see that the intersection is such that the object is formed at the same place C, but of course, now it is inverted image. The image is formed at the same place as C, and it is an inverted image. We will see subsequently, it appears here that the object size is the same as the image size. We will see this later mathematically, that indeed it is true. So, these are some of the geometrical ways in which we can obtain the location of the image for a given position of the object. However, in practice, every time we cannot be drawing images to find drawing these rays to determine the position of the image. In an optical system, particularly in a compact optical system, it is very important that we locate these images very accurately, and we have to know the exact magnification of the object which we achieve, and therefore, there has to be some analytical expression to obtain the location of the mirror, location of the image, and this leads us to the mirror equation. So, let us analytically discuss the formation of the image, reflection by a concave mirror. So, as before, consider a linear object A B here located in front of a concave mirror. So, as shown in the figure. So, I will try to draw this figure several times in the next few slides, and as we see that B P is the distance where the object is located from the mirror, and therefore, it is called object distance normally designated by small u, object distance. The image is formed A dash B dash, which is here, and this distance B dash P is called the image distance and denoted by V. Cp, C to P, C is the center of curvature, therefore, this distance is the radius of curvature. Cp is equal to radius of curvature and denoted by R. Fp is the focal length, this is the principal focus. So, Fp is the focal length denoted by F. AB, the height of the object or the size of the object, here it is a linear object and therefore, the height is the same as the size and height of the object is H denoted by H and height of the image A dash B dash is denoted by H dash. So, before we discuss the formation of the image, a very important point to remember is to follow the sign convention. The sign convention is very important. We have to follow a sign convention so that the formula that we will derive subsequently, the formula that we will be deriving will be applicable for all cases. By all cases I mean whether it is a concave mirror or a convex mirror, whether the object is in front of the mirror at a certain location or another location, the formula will remain the same. The formula for the magnification will also remain the same. So, that is why we have to follow this sign convention. So, the sign convention, what is this sign convention? We follow the Cartesian sign convention. So, here is the object. So, I have just dropped the ray diagram, rest is the same, the object AB is here, the image A dash B dash, center of curvature, principal focus, pole. Now, in the Cartesian sign convention, the principal axis is positive, or let us say it is the x axis, then x is positive in the direction of the incident light. That is, if the light is incident from the left, then x in this direction is positive, and y of course, here is positive and in this direction it is negative. Therefore, all distances are measured with respect to the pole. All distances are measured with respect to the pole, that is this point, x equal to 0, y is equal to 0, which means if we measure the distance to this side, these are negative, that is the distances are measured in terms of the coordinate of the point with respect to the pole, that is coordinates of the points B, C, B dash, F. These will be the distances. Distance as such is not a negative quantity, but because of the for the sign convention we consider that the distance here is negative depending on the coordinate of the point. If I had a distance here, for example, if I had a image or something on this side, if I were to have a virtual image, as an example let me show that, suppose I were to have a virtual image here like this, A dash B dash, then the image distance would have been this. So, this would have been the image distance. Now, this is in the positive x direction, because this is x equal to 0 and therefore, the image distance would have been negative. But in the diagram that I have shown corresponding to the case which we have considered, we see that BP here is equal to minus u. U is the object distance, but it is minus u because it is on this side. Similarly, Cp is equal to minus r, B dash p the image distance is minus v, and Fp the focal length here is minus f. Any distance above, that is the length here h is positive and in the negative y axis is negative. Therefore, AB, that is the size of the object here, is positive h, and A dash B dash is minus h dash. H dash is the size of the image, but A dash B dash is minus h dash because of the sign convention. It is below the x axis in the y direction. So, with this sign convention we proceed further with our problem, and then we will apply it to other cases as well. So, coming back, reflection by the concave mirror, look at this diagram, this is the ray diagram. So, I have marked with the dotted lines to identify certain triangles. First, the triangle A dash B dash F, this triangle here A dash B dash F, and triangle F M D, M is the point here where the parallel ray is incident, D is the point here where a perpendicular is dropped on the principal axis. So, F M D. So, this triangle are similar, because we can see that this angle is the same as this angle, opposite angles, these are 90 degrees, therefore, all three angles are the same, and therefore, we have A dash B dash by M D, that is A dash B dash by M D, the ratio is equal to B dash F by F D, B dash F by F D. Actually, these angles are the same, therefore, tan theta is the same. So, tan theta is basically A dash B dash by A dash here. So, A dash B dash by A dash F. So, the tan theta is the same, which gives you A dash B dash is equal to B dash F by F D. And therefore, A dash B dash by A B, because M D is the perpendicular dropped here, and therefore, M D is the same as A B, and therefore, A dash B dash by A B instead of M D A B is equal to B dash F by F D. So, let me denote it as equation number 1. Now, we look at the other two triangles. So, the other two triangles which I have marked here, that is A B P and A dash B dash P, A dash B dash P. These two triangles are also similar, because these are 90 degrees, here the angles are equal because it is reflection taking place here. So, these angles are equal, therefore, these angles must also be equal. So, all the three angles are equal, and therefore, the ratio of A dash B dash by A B must be equal to B dash P by B P. A dash B dash divided by A B must be equal to B dash P divided by B P, that is the ratio of the sides. So, A dash B dash by A B is equal to B dash P by B. So, let me denote it that equation 2, and therefore, from 1 and 2 this left hand side are the same, and therefore, we have B dash F by F D is equal to B dash P by B P. Let me call this as equation 3. So, let us proceed further. For small aperture, in the last class we had this discussion on paraxial rays, and I had also said that the small aperture approximation is the same as the which lead to paraxial rays remaining inside the optical system, and therefore, for small apertures we are dealing with paraxial rays, and for small apertures therefore, M is close to the axis. Small apertures means all the rays are close by. This point M is close to the axis. I have shown here a little further off just to get a clearer image, otherwise this M is close, paraxial or small aperture approximation, M is closer to P, which means if I draw a perpendicular here, the point D will be close to P. So, for small aperture M is close to the axis, and therefore, that implies D is close to P, which means F D here is nearly equal to F P, because D and P are very close, and therefore, F D is the same as F P. Also, B dash F, note that B dash F here is equal to B dash P minus F P, and therefore, substituting these F D nearly equal to F P and B dash F is equal to B dash P minus F P, equation 3 becomes B dash P minus F P divided by F P. Please see equation 3. So, equation 3 is here. So, B dash F by F D we had. So, F D is the same as F P, and B dash F is B dash P minus F P, and therefore, we have the equation. Now, we apply the sign convention. Sign convention we have already discussed. For this example, therefore, the sign convention B dash P is the image distance which is on the left. We are all the while treating light incident from this direction. Therefore, our x axis is increasing in this direction, x equal to 0 is here, and therefore, b dash p is minus v. The coordinate of b dash is minus v. So, minus v minus f p, f p is minus f, the coordinate of f is minus f divided by f p minus f, which is equal to minus v by minus u, b dash p divided by b p, b p is minus u, and therefore, so this gives, so you can simplify this of course. So, quickly you can simplify here. So, this is minus v by minus f minus f minus f by f, which is 1, which is equal to minus v by minus u, which is v by u, and therefore, this is v by f. So, I take this to the other side. So, we have v by f minus v by u is equal to, this 1 goes to the other side. So, 1 or v into, which implies v into 1 over f minus 1 over u is equal to 1. V goes to the other side. So, we have 1 by v on the other side, and therefore, we have, and I take this to the other side. So, we have 1 over v plus 1 over u is equal to 1 over f, which is the mirror equation. So, this is called the mirror equation. So, very simple, we have 4 equations, very quick. So, we have considered the equivalence or the similarity of these triangles and found out the ratio of the a b to a dash b here. So, a dash b dash to a b, which comes out to be this, and then we have from the other triangle we get that equal to b dash p by b p, equating the 2 we get this. Then we use the small aperture approximation to get f d nearly equal to f p, and observe b f is equal to b dash p minus. Substituting into 3 we get this equation, and simply apply the sign convention and substitute the relevant quantities, and we have the mirror equation. The mirror equation tells us that if you know any of the 2 quantities, then the third quantity can be determined. For example, when the mirror is given, normally the radius of curvature or the focal length of the mirror is given, and you may be knowing the object distance and asked to find out the image distance, or an image distance may be given and you may be asked to find out the object distance, which means the third unknown can be determined using the mirror equation, and one can precisely determine the location correct to the accuracy that is required, of course, all within the small aperture approximation. Now, let us go further and discuss about the lateral magnification of the object. When the image is formed, we would be interested to know whether we will get a magnified image or a contracted image or a demagnified image. So, here lateral magnification, which is also called linear magnification, because we have considered a linear object and only in the lateral direction, transverse direction, and therefore, m, the magnification is defined as size of the image by size of the object. Size of the image is h dash, size of the object is h here, a b size is h, and h dash size of the image is the same figure I have drawn, again dropping the ray diagrams there, and locations are pointed out. And from equation 2, we had equation 2 here. So, earlier we had derived the equation 2, we had obtained the equation 2, a dash b dash by a b is equal to. So, I have rewritten that equation 2 here, because a dash b dash. So, applying the sign convention, h dash here, a dash b is on in the negative y axis, along the negative y axis, that is below the x axis, and therefore, this is negative quantity, and therefore, we substitute minus h dash divided by a b, which is h, is equal to b dash p as before is minus v divided by b p, which is minus u. So, substituting here, we get m, the magnification is defined as h dash by h is equal to minus v by u. This formula holds good for all cases, because we have already applied the sign convention. Now, for the present case, you can see here that the magnitude v is smaller than the magnitude u, and therefore, v by u is less than 1. So, the magnification m mod m, that is the actual ratio of the sizes, is less than 1, which implies we get a demagnified image. So, we can see in the diagram as well, the ray diagram earlier which we had drawn. So, we can see it very clearly that this size is larger and the image size is smaller, and mod m is less than 1, which implies it is a demagnified image. The negative sign here, the negative sign m, if we were to get a negative sign in the magnification, that implies it is an inverted image. Negative sign implies inverted image. So, we will see this further. So, let me take another example here very quickly to show that when do we have a magnified image and when m is positive. So, I have now considered the object between the principal focus and pole. So, AB is here, a parallel ray goes in this direction. Here the ray to the pole gets reflected in this direction. As before, as discussed before, these two do not intersect in this direction, but they appear to come from a point here A dash, and therefore, A dash B dash is the size of the image here, which is h dash. Now, note that h dash is positive here, that is A dash B dash is positive, A B is also positive. Therefore, m is equal to A dash B dash by A B is greater than 1. We can see it very clearly, it is greater than 1, and we have a magnified image. And this is also a positive, A B is also positive, A dash B dash is also positive, which implies m is positive. That this happens when we have an erect virtual image. So, when the magnification is positive, it means the image is erect. So, erect virtual image. How about getting a magnified real image? Yes, we can also get a magnified real image. So, we started with the problem where we had assumed the object to lie between C and F. If you take the object, we had started to consider the object beyond C. Instead, if we had taken the object between C and F, so if you draw the ray diagram, you can see that you will get an image beyond C, which is a magnified real image. So, magnified real image, but an inverted image which is beyond C is also possible for real images. Let me take an example of the sign convention for convex mirrors, because so far I have been discussing mainly on image formation by concave mirrors, but I have emphasized that if we follow the sign convention, then the formulae that we get are applicable to both cases, that is whether it is a convex mirror or a concave mirror, whether it is a real image or a virtual image, the formulae are applicable. And therefore, let me take one example of the sign convention in the case of a convex mirror. So, there is a convex mirror here and there is an object A B in front of it. So, the parallel ray which is incident here is reflected such that it appears to come from the principal focus here, and a ray which comes to the pole is reflected in this direction, and as we can see both the rays are diverging away on the left side of the mirror, and therefore, there is no way that they will intersect, but if we extrapolate this onto the other side of the mirror, then they appear to come from the point A dash, and therefore, an image is formed, a virtual image is formed, a virtual image A dash B dash is formed on the back side of the mirror at a certain distance. But the main point to see is now H dash is positive, H is positive, and if we BP the object distance BP is negative because it is in front of the mirror, and x equal to 0, y equal to 0 pole is here, therefore, B p is minus u, but B dash p here this distance where the image is formed is positive. So, B dash p is equal to V, F p the focal principal focus is here, F p is positive and C p is positive, and therefore, A b is equal to h, A dash B dash is equal to h, and therefore, if we substitute in equation 2, which is this A dash B dash by A b equal to B dash p by B p, we get h dash by h is equal to V by minus u, or m is equal to magnification m is equal to size of the image by size of the object is equal to minus V by u as before. As before here refers to the problem of concave mirror where we had seen. So, this illustrates that the formula that we get will hold good if we take appropriate sign convention, whether it is a convex mirror or a concave mirror. Right. So, let us take an example now. So, an example from the textbook. So, I have taken here an example from the textbook is a very simple example, but there is a purpose of taking up this example. So, a linear object is placed in front of a concave mirror of radius of curvature 15 centimeters. What will be the position and magnification of the image if the object distance is 1 10 centimeter, 2 5 centimeter in front of the mirror? So, the problem is here. So, let me work this out for you. So, let us work it out. So, the problem says a linear object is, so here is a concave mirror. So, as soon as the problem is given a concave mirror, the principal axis, so this is the principal axis, the radius of curvature is 15 centimeters, it is a concave mirror, therefore, the radius of curvature is 15 centimeters is here. So, this is the point C, and because it is in front, so we have R is equal to minus 15 centimeter radius of curvature. The next data given is, first let us consider the object at a distance of 10 centimeter. So, the focus here we have already shown f is equal to r by 2. So, this is the principal focus, therefore, f is equal to minus 7.5 centimeter. The object is, first the object is at 10 centimeter distance in front of the mirror, and therefore, the object distance u is equal to minus 10 centimeter, minus 10 centimeter. So, immediately, so the object is somewhere here. Let me take this as the object A b, and this point is minus 10 centimeter here. So, use the mirror equation 1 by V plus 1 by u is equal to 1 by f. So, that is 1 by V, V we do not know. So, the question is what will be, so we are supposed to find out what will be the position and magnification of the image. So, the if the, so what we need to find is V is equal to how much and m is equal to how much. So, 1 over V is equal to 1 over f, I will take this to the other side, 1 over f minus 1 over u, which is equal to f is, so 1 divided by minus 7.5 minus 1 divided by minus 10, 1 over u. So, that is equal to, let me work it out here very quickly. So, this is positive, and therefore, we have 1 over V is equal to 1 over 10 minus 1 over 7.5. So, that is equal to 10 into common denominator 75 here, and this is 7.5 minus 10, which is equal to minus 2.5 divided by 75, which is equal to minus 1 divided by 2.5 goes 30 times. So, 30, or V is equal to minus 30 centimeters. So, what does this mean? So, if I keep this, so this was at, this is 15 centimeters minus, this is minus 7.5, this is minus 10, which means the image is formed at a distance here at, so the A dash B dash, the image distance is minus 30 centimeters. So, this is where B dash will be formed. So, this is what we know now, right now, and therefore, M, the magnification. So, we take up magnification M is equal to minus V by U, which is equal to minus of minus 30 by minus 10, U is minus 10, which is equal to minus 3. So, the negative sign indicates we have a inverted image, and M, mod M is 3, which is M greater than 1. So, this implies we have an inverted and magnified image, 3 times magnified image. In fact, this was the question which I asked, can we have a magnified image? Yes, as we can see when object magnified real image. So, the object, so this is what we have, 3 times magnified A dash B dash is 3 times A B at a distance of minus 30 centimeter. Very simple example. So, the first part is for 1, U is equal to minus 10 centimeter, and second at 5 centimeter. So, let us take the second one 5 centimeter very quickly. So, second U is equal to minus 5 centimeters. So, as before 1 over V is equal to 1 over F minus 1 over U, which is equal to 1 divided by minus 7.5 minus 1 divided by minus 5, which is equal to 1 by 5 minus 1 by 7.5 here, and that is equal to, so 5 into 7.5 here. So, that is 37.5, and 7.5 minus 5, which is equal to 2.5. So, 2.5 divided by 37.5, which is equal to, coincidentally this is also 1 over 30. 2.5 25, sorry, this is 1 over 15, 1 over 50. 25 goes, so this is 25 divided by 375, or V is equal to 375 divided by 25, which is equal to 50, which is equal to 50. So, we see that therefore, M magnification is equal to minus V divided by U is equal to minus 15 divided by 5, which is equal to minus 5. U is minus 5. So, minus 15 divided by minus 5, which is equal to 3. We have got the same magnification now. Earlier also we had a magnification of 3, but it was a real image, but now we have a magnification of 3, but this time it is a virtual image, a magnified virtual image. This is obvious for us that because right now we have, so let me keep the diagram. So, we have, where is the diagram? One second. Yeah. So, let me draw it again. So, here it is. So, this was f was 7.5, this was minus 7.5, C was minus 15. Now, we have the object at 5 centimeter, that is u is minus AB. So, this is minus 5 centimeters, minus 5. So, we know that when the object is between the principal focus and the pole, we get a magnified virtual image. So, that is what we have. For the second case, we have u is equal to minus 5 centimeter, we have a magnified image 3 times magnified, but it is a virtual image. There is no negative sign here, which means it is an erect image. Now, let me extend this example. So, this is the example which is there in the book. Now, if I extend the example further, so extend the example. For 2 more distances, for 3, for u is equal to minus 15 centimeters, and 4 for u is equal to minus 20 centimeters. We have seen for u is equal to minus 10 centimeters and u is equal to minus 5 centimeter. In one case we had a magnified real image, and in the other case we had magnified virtual image. Now, if so, let us take this as well, just it is a very simple example, but it conveys certain things. So, 1 over v is equal to 1 over f minus 1 over u, and if we substitute this 1 over minus 7.5 minus 1 over minus 15 is equal to 1 over 15 positive minus 1 by 7.5 is equal to 1 by v. So, 15 is the common denominator. So, we have 1 over v is equal to 15 here, and we have 1 minus 2 is equal to minus 1 by 15, which is equal to minus. So, this implies v is equal to minus 15 centimeters. So, what is 15 centimeters? Minus 15 centimeters is the radius of curvature. It is given in the problem that minus 15 centimeter was the radius of curvature. So, let me check where the problem is. So, here is the example. It was given that the radius of curvature is 15 centimeters, and therefore, we got when the object is at the radius or placed at the radius of curvature, the image is also formed at the radius of curvature. So, here it is, and what would be m? The magnification will be minus v by u. So, both are same, and therefore, the magnification m will be equal to minus 1. What does minus 1 means? Minus means it is inverted, m is equal to 1 means neither it is magnified nor it is demagnified, and therefore, we have the image here. So, the object was at the radius of curvature here. So, this is point C, and we have got the image also right here at the same place, inverted image. So, this is A dash and this is A, and this is of course B and B dash. If we take the fourth one, simple exercise, of course, the problem is extremely simple, but why I am doing it. So, if we take the fourth one very quickly, that for u is equal to minus 20 centimeters, I will straight away give you the answer. So, we have 1 over v is equal to 1 over f minus 1 over u. So, this substituting should give you v is equal to let me see, should give you u is equal to, let me check whether I have the answer. All right, it does not matter, we can find it out immediately. So, 1 over f minus 7.5 minus 1 over 20 for u is equal to. So, this is minus 20, which is equal to 1 by 20 minus 1 by 7.5 here. So, that is equal to 20 into 7.5. So, 20 into 70. So, this will be 20 into 7.5, which is nothing but 150, 20 into 7.5 and 7.5. So, 20 goes 7.5 times in this. So, we have 7.5 minus 7.5 goes 20 times in this, and therefore, this is 20. So, 7.5 minus 20, which is equal to minus 12.5 divided by 150, 12.5 divided by 150, or v is equal to minus 150 divided by 12.5, which is equal to 12, minus 12 centimeters. So, when u is greater than the radius of curvature, please see that r is equal to minus 15 centimeters, then the image is formed at a distance of minus 12 centimeters, that is between the radius of curvature and the principal focus, and the magnification m is equal to minus v by, so minus 12 minus of minus v by minus 20, which is equal to minus 0.6, minus 0.6. This implies it is an inverted image and the mod m is less than 1, which means it is a demagnified image. Now, these 4 cases, the 4 cases that I discussed right now are by chance they happen to be the same 4 cases which we had discussed earlier. So, when it was here, we got a demagnified image. So, the case of a magnified image, 3 times magnified image when it was in between, the case of magnified image 3 times, but a virtual image, and the third one when the distance was equal to radius of curvature, we get the inverted image right there. All of this is obtained purely by geometry, but from the numerical example we get the same, and therefore, geometry is fine. Geometry is good to give you an idea when the numbers are given where you are likely to get the image. It will tell you immediately, so that by chance when you do a numerical, if you make mistake, then you can always cross check with your concept, saying that yes, I am supposed to get it somewhere here. The exact number, to get the precise location of the image and to obtain the precise value of the magnification, we have to use the mathematical formula, but the geometry will tell you an idea about where it is. Sometimes we might make an error in the numerical calculations, and then you can always cross check, oh no, I am expected to get this image here, but I did not. So, there is something wrong and immediately you might have missed one negative sign or something. So, that this helps you in cross checking your calculations. Now, before we close, I would like to keep one important note, that when we solve all the problems, we must keep in mind the following. Note, the mirror equation was 1 by u plus 1 by v is equal to 1 by f was obtained by substituting the coordinates corresponding to the positions of the object, image and the principal focus. Therefore, in using the mirror equation to determine the unknown parameters u or v or f, as in any numerical problem, the coordinates corresponding to the known parameters must be substituted. We should take care of this whenever we have a numerical with a concave mirror or a convex mirror. So, to summarize what we have discussed today is first, so let me just summarize here. To form a image, so formation of image, we need any two rays. So, any two rays intersecting after reflection. That will give us the point. Then we have derived the mirror equation 1 over v plus 1 over u is equal to 1 over f with proper sign convention, and of course, the magnification, lateral magnification or linear magnification is equal to minus v divided by u. So, we will discuss further as we go into the next class. Thank you.